Hello everyone, today we're gonna perform our experiment number 4 for our Power Electronics Laboratory, which is entitled Half-Wave Rectifier with RL Source Load and Inductor Source Load. The objectives of this experiment are to simulate the half-wave rectifier with RL source load using PSpice software, to utilize the software to observe the behavior of half-wave rectifier with RL source load, and to determine the power quantities using PSpice software. Now let us proceed with our experiment. So first, open OrCAD and create new project. For the first part of the experiment, we will use an RL source load. So first, let us build our circuit. Then edit your components. For the sinusoidal voltage source, it is required to use a voltage source with 220 Rms. So we will be using a 311.13 peak voltage. Frequency is 60 Hz. AC is 0. D break for the diode, and resistor will have 2 ohms, while our inductor would have 20 millihenries, and our DC voltage source would have 100. So now edit your simulation profile, save, and edit the parameters. Since our frequency is 60 Hz, this would be 16.67 milliseconds, since 1 over 60 is 16.67 times 10 to the negative 3, and maximum time step should be 10 microseconds. Click OK and run. Let's add again average power across the resistor. The average power across the resistor would be 553.801 watts. Now let us add our average power across the DC source. It can be measured at the end of every cycle. So seeing that the average power across the DC source is 1.0815 kilowatts. So these are the two waveforms asked for this part of the experiment. To better understand the experiment, it is observed that the waveforms do not instantaneously start at 0 seconds, because they are at 0 watts at 0 seconds. So to understand it better, we should add the AC source and the DC source. These two, the yellow and the blue waveforms, are the voltage waveforms for the AC source for the blue and the DC source for the yellow. It can be seen that at their intersection, the waveforms for both the average power of the DC and the average power across the resistor starts to build up. So moreover, we can see when we add the voltage waveform of the resistor. From here, we could see that once that a certain voltage is reached for the diode, the diode turns off, because it will be reverse biased, and the only source active in the circuit would be the DC source, because we can prove this by looking at the point here. from here, we could see that the voltage waveform across the resistor becomes stable at 100 volts when the diode is off. Since when the diode is off, the AC voltage is cut off, and the only source providing voltage for the circuit would be our DC source, which is 100 volts. To add, once that the blue waveform, which is the AC voltage, and the yellow waveform, which is the DC voltage, intersects, this means that our diode starts to conduct, which means that there would be two voltage sources providing power to the circuit, which is why there would be two build-ups for the waveform across the average power of the DC source and average power across the resistor. Then lastly, to add, we could add the average power across the inductor. We could see that the average power across the inductor is represented by the light blue waveform. And once that the average power of the inductor drops to 0, this would be the time when the diode turns off and the voltage becomes stable at 100 volts. So to recap, the average power across the resistor would be 553.801 watts, and the average waveform across the DC source would be 1.08 kilowatts. Now let us proceed to the second part of the experiment. So let's add another page. Page 2. So the second part of the experiment would use a circuit with an inductor and DC source. So let's remove the resistor used, and since there would be same configurations for the circuit, wherein the VRMS would be 220, which is equivalent to 311.13 Vmax, frequency of 60, D break for the diode, and 20 millihenries for our inductor, and 100 volts for our DC source. The simulation profile would also be the same, 16.67 milliseconds for the runtime, and maximum step size of 10 microseconds. So let us simulate. First, we are asked to record the RMS current across the DC source. So it would be DC1, IV DC1. We use DC1 because the first part of the experiment already used VDC. So as an addition, the DC source is automatically renamed VDC1 for the second part. So now to determine the RMS current, the RMS current flowing through the DC voltage source, we would see it at the end of one cycle, which is at 16.67 millisecond point. So the RMS current is 23.073 amperes. Now we are asked to add the power absorbed by the DC source. So it will be WVDC1. As we can see, there is a large difference between the two values, since the RMS current only became a straight line, almost a straight line. This means that the power across the DC voltage source is extremely large. So at the end of one cycle, DC power would be 106.364 nano, while its peak value is 4.4142 kilowatts. To better see it, let us add the average power across the DC voltage source. So at the end of one cycle, we could see that the average power is 1.5690 kilowatts for the DC source. This is bigger than the circuit with the inductor resistive source load because it is greater by almost 500 watts. Now let us remove this and let's add another plot at trace. Now let us add the DC voltage, the AC voltage, and let us also add the voltage waveform across the inductor. So once again, at this point of intersection here, we could see that this would be the part where the waveform starts to rise. So seen from the DC power, it's when the DC voltage and the AC voltage intersects or have equal value. So upon achieving equal value, the diode turns on, which means it's conducting and is able to produce a waveform. On the other hand, upon reaching a certain voltage, so in this case it would be upon reaching negative 287.561 volts, the diode turns off. Which means it would stop conducting. If it stops conducting, the only voltage source would be our DC voltage source. That's why the voltage waveform becomes a steady 100 volts voltage. So we could check this by looking at cursor blue. So here we could see that the DC voltage is at 100. Also, upon turning off the diode, it is seen that the DC power decreases. And if we would remove this, we could see that the RMS voltage across the DC source also decreases. So let us put back our DC there. So to recap, the red waveform on the second panel is the waveform for the power across the DC voltage source. On the other hand, upon removing it, this would be the RMS current across the DC source, which is 23.073 amperes. And once that the diode starts conducting, the DC voltage waveform would start to rise. And as the AC source reaches a certain voltage, which is negative 283, which is the cut-off voltage for the diode would turn off, which means only the DC source would be the active voltage source for the circuit. This means that the power waveform across the DC source would slowly degenerate or become less in value. Conclusion. The experiment was conducted using OrCAD Capture CAS Lite for building circuit and PSpice AD Lite for running the simulation. It was observed during the experiment that the diode determines the flow of the voltage and power provided by the AC voltage source attached at the initial part of the circuit. When the AC source produces a voltage higher than 100 volts at certain points in time, The diode conducts since the anode voltage is greater than the cathode voltage, meaning that the diode would be forward biased. Upon reaching a certain voltage, the diode turns off and becomes reverse biased, which leads to the DC voltage being the only remaining active voltage source for the circuit. The circuit is considered as a rectifier circuit because it only allows the AC voltage to pass at certain points in time and not pass as a whole waveform. This occurrence is determined by the component characteristics of the diode. On the other hand, the circuit does not fully become off due to the presence of the inductor, which prevents drastic change in current flow. Therefore, the presence of an inductor in any rectifier device which requires a regulated current flow is essential.